back to Maths with Mrs. J. We've started a series of videos about integration. We talked about the fact that integration is the same as anti-differentiation, which means that you're going back in the other way. We talked a little bit about some of the reasons why we might want to integrate. One of those being finding areas between curves or areas between a curve and the x-axis. Or perhaps we're going from a function for acceleration to the function for velocity. Then we did a video on how to actually anti-differentiate by rule any sorts of polynomials. We also did some examples where we had a product or a quotient, and I said that if you can possibly avoid dealing with those, do avoid dealing with them. So if you have something that you can easily expand to make it a sum or difference, go with that first. If you have a quotient where you can easily divide through, do that first and then integrate. Today I wanted to talk about what I refer to as the chain rule in reverse, which will be a recurring theme throughout our integration videos. But today I'm just talking about it when what we refer to as the inner function, this is our inner function here, is linear. Ax plus b is a linear expression. The derivative of ax plus b is just the constant a. So if I were to differentiate that, I would get n ax plus b to the n minus 1. Remember, we bring our index down as a multiplier, decrease it by 1, but then the chain rule says that we also have to multiply by the derivative of that inner function, which in this case is just the constant a. So you end up with that. Now, if we're going in reverse, which is what integration is, if we have a linear function as our inner function, we know that the derivative of that is just a constant. We're allowed to multiply or divide by constants when we're integrating or differentiating without having to worry about any sorts of special rules. It's just a constant number that I guess comes along for the ride, you could think of it. So imagine if we had x to the n and we were integrating, we would increase the index by 1 and divide by the new index and have our constant term coming in there. The only difference here is that we need to also divide by the derivative of that linear function. I call this the chain rule in reverse because really what you're doing is up here, using the chain rule, you'd have to multiply by a. So here you're going to divide by a. Now let me just stress here, what we're doing today is just working with linear functions where the derivative of the inner function is just a constant term. If you were to have an inner function of something like x squared plus 3, you can't then just divide by 2x or do something like that. We will talk about how to deal with examples like that further down the track. All right, so for today, we're just dealing with ones where the inner function is linear. All right, let's have a look at some examples and see how we go. All right, first thing is the inner function linear? Yes, it is. What is the derivative of 3x minus 4? It's just 3. It's just a constant number, so it's not a problem. So using our normal rule, we're going to increase our index by 1 and divide by the new index and have our plus c. But to take into account the fact that this wasn't just an x, it was a function involving x, a linear function involving x, we also need to divide by the 3. So just tidying this up a little bit, we end up with that. Okay, let's try a couple more examples. Now these ones, you might recall from when we were doing differentiation, I said that it's a good idea, or in fact it's necessary really, to change to index notation before you start doing anything else with it. So we're still going to write the integration sign here, and we're just going to change this to index notation. Square root is the same as having an index of a half. Now we're in a position where we can go ahead and do our normal thing. This is just linear, so it's okay. So we're going to get 2 times 4x plus 5 to the 3 on 2. Remember, we increase our index by 1, divided by the 3 on 2, divided by 3 on 2, I should say. And we also need to divide by 4, which is the derivative of that inner function. Now that looks like a bit of a mess, but it actually comes out quite nicely. This 2 comes up here, the 2's will cancel with the 4, and you're actually left with 4x plus 5 to the 3 on 2 over 3 plus your c. If I just had x to the 3 on 2, I'd tend to change that to x root x, but because we've got a whole expression here, I'll probably just leave it with the 3 on 2. All right, last one for this video. Again, keep the integration sign at this stage because we're going to change this to index notation. If you have 2x plus 1 cubed in the denominator, that's the same as 2x plus 1 to the negative 3. So that's our first step before we even try to do any integration. All right, now we go about the normal process. 2x plus 1, increase the index by 1, divide by the new index, but we've also got to divide by the derivative of that linear function. All right, this is a linear function that we're working with, so the derivative of it is just a constant, so it's perfectly okay to just divide by it. All right, tidying up a little bit, if that's to the negative 2, we've got that squared in the denominator, and we've got a, negative 5 in the top over 4. I'll just move that 5 down a smidge. And away you go.